Greetings. We will begin unit 4 today. This will be on the many electron systems. We did the hydrogen atom, the non-relativistic hydrogen atom first, and then the relativistic hydrogen atom. We did the Dirac formalism of the hydrogen atom as well, and we were very fortunate in dealing with this because the one electron Coulomb problem has exact solutions, and we got the exact solutions for the hydrogen atom, both for the non-relativistic case as well as the relativistic case. So, atoms in general, other than the hydrogen atom, they have more than one electrons, and 2, 3, 4 and so on, and you have got the whole periodic table. So, we need to develop the quantum mechanics of many electron systems, and this is really important because atoms in a certain sense are the basic building blocks of condensed matter. So, when atoms come together, you have molecules, clusters and condensed matter. So, in some general sense, you can even say that the atom is like what elementary particle is, somewhat similar in a certain sense, that it is the elementary ingredient of condensed matter. So, all properties of condensed matter are derived from the properties of atoms and from their collective behavior, and we need to understand that when you have more than one electron present, then these electrons are going to interact with each other, and we will talk about electron interactions with each other and also electron correlations. And I will make a distinction between interactions and correlations. This difference will become clear as the discussion progresses, because correlations has got a specific connotation which will become very clear. And in particular, I will talk about two different kinds of correlations, one which are known as exchange correlations, and another kind of correlations which are known as Coulomb correlations. So, we will talk about both of these in this unit. So, these are our primary learning goals, and we will approach this from first principles as much as possible, and we will be extending the quantum mechanics which was developed by Einstein, Schrödinger, Heisenberg, and applied to atomic systems by Niels Bohr. And then when it comes to the many electron formalism, we will talk about the work of Hartree and Vladimir Fock. So, this is our goal for this unit. I will be using Betty and Jacque's intermediate quantum mechanics rather extensively for this unit. It is a book which many of you would have used for basic quantum mechanics. I will also use Branston Joshain's book Physics of Atoms and Molecules, and there is a small review on the Hartree-Fock method which I had written with two of my colleagues, which is uploaded at the course web page, which also you can access, where some of the key features would be summarized. Now, this is the relationship that we have to address. So, we will first work with the non-relativistic many electron problem, and the Schrödinger equation will read H psi equal to E psi for the n particle system, n being the number of electrons that we have in the system. So far so good, but immediately we meet new difficulties. And what are these new difficulties? What these new difficulties do is to create a situation which can perhaps be called as a catch-22 situation. Do you understand what catch-22 means? Okay, catch-22, actually this phrase comes from a novel by Joseph Heller, and it made so much impact on the English language that it actually became accepted in the English language as a regular phrase. What it means is that you have a situation which has got some internal inconsistency. Okay? You can describe the situation, you can seek to solve that situation, to address that situation and find some sort of solution, but the solution becomes impossible to be implemented because of some internal constraint which is intrinsic to the system. It is a very fascinating novel, and actually the situation in this novel is about an Air Force pilot who does not want to go into hazardous duties, and he wants to escape from it, and he discovers that he can escape from it on one ground, that if he is not psychologically fit, mentally fit to execute, then he will be relieved. So there was such a provision. So he applies, he asks to be relieved under that situation, and then they say that okay, if he is sane enough to say that he wants relief because of this reason, then obviously he is not mentally sick. So it is a provision which is inbuilt into the situation, right, and this is the catch 22. So there is a catch, and the many electron problem poses itself as a catch, and I will tell you what the catch is. So let us look at the n electron Schrodinger equation. Now you set up the Hamiltonian for the n electron problem, which is the sum of the kinetic energy part. Okay, I have not written the mass, which is in natural units, put m equal to 1, h cross equal to 1. Okay, so this is the kinetic energy term. Okay, and then this is the potential energy of each electron in the field of the nucleus. There are z protons in the nucleus, so each electron would experience an attractive potential which is z over r, and you would sum over I going from 1 through n, and then each electron would repel the other electron. So between the ith and the jth electron there would be the 1 over Rij Coulomb repulsion, and you must sum over all the I and j, I not equal to j, right. So this is the Coulomb repulsion of between every pair of electrons. So this is your n electron Hamiltonian. Now look at the system. If you have electrons in the atom, so you have got the z protons in the nucleus, and then you have got this 1 over Rij term which is between the ith and the jth electron, between every pair. Now this is the distance between the ith and the jth electron. Okay. Now the problem is that electrons are not classical particles. Okay, so they are not like point charges, and you cannot say that okay, this is where the ith electron is located, this is where the jth electron is located, and this is the distance between them. Now that is how you would describe the classical Coulomb interaction between two classical charges. Now the electrons are not like that. Electrons are described by waves in quantum mechanics. So they have a certain wave function associated with each electron, which is the probability amplitude function, as we know, right. Corresponding to this probability amplitude there is a probability density, and this multiplied by the charge density is what would give you the charge at in a certain volume. So if you got a certain volume element over here, delta V, and in this delta V you find out what is the probability density integrated over the volume, that will give you the charge over here, and then this charge would interact with a corresponding charge over here, which is also to be described in terms of the probability density over here, and then these two charges would interact with each other, giving you the 1 over Rij term. Now that is precisely the catch, because to describe the charge density over here, do not you need the wave function for the electron? You do, right. And how were you hoping to get this wave function? By solving the Schrodinger equation. Okay. So you set up the Hamiltonian, right, solve the Schrodinger equation and hope that okay, I will now get the wave function, and use this wave function to describe the probability amplitude, the probability density and the charge density. But you need the solution even to pose the problem. Okay, that is the catch 22. So, you are caught up in a situation that you need the Hamiltonian to get the wave function, but to constitute the Hamiltonian, to formulate the Hamiltonian, you need the wave function. Okay? And this is a vicious circle, and if you do not know how to deal with it, the easiest thing to do is to quit physics and walk out, or else come up with some very nice innovative ideas. Okay? And this is where self consistency comes in. What you can do is, okay, I do not know the wave function and therefore I cannot construct the Hamiltonian. So, let me make an assumption on the wave function. I will make a guess, does not matter if it is wrong, let me make a guess, and using this guess wave function I kickstart the process. Using this guess I construct the Hamiltonian. Now, using this Hamiltonian, which is based on a guessed wave function, I now solve the Schrodinger equation and get the solution, and now I ask, is this solution the same as what I had guessed? If it was, I got lucky. If not, no problem, I will change my guess. Okay? And then reconstruct the Hamiltonian with a new guessed wave function, then solve the Schrodinger equation, and then ask, is the new solution the same as my improved guess? It could actually be worse, but it could be better. And you iterate on this process again and again and again and again till you hit self consistency. Okay? Now, that is the trick, and once you get this self consistency, you can then say that now you know what the Hamiltonian is, and now you know what the wave function is, and you get the two together when you reach self consistency, and then use that wave function to describe other properties of the atom, and then do spectroscopy with these atoms or electron structure analysis, collisions and so on. So, these solutions can be obtained numerically by carrying out this iterative process, and this was a technique which was developed by Hartree, Dr. Hartree at Cambridge, and initially Hartree did not take into account the electron spin, but then there is this spin which we know has to be taken into account, and then the formalism of self consistency which was developed inclusive of the electron spin is what we call as the Hartree-Fock formalism. That is something to which Vladimir Fock contributed significantly. So, that is the overall technique of Hartree-Fock, and I will essentially the difficulty is summarized on this slide, that setting up the Hamiltonian itself requires the very same solutions which you hope to obtain by solving the Schrodinger equation. So, that is the difficulty that you are now going to address. So, this is our many electron Hamiltonian. This has got a formal structure, okay, and the summation over the Coulomb repulsion terms can be written either as this or half of this double summation with I and j going from 1 through n, but I not equal to j. So, these two ways of writing this Coulomb repulsion is completely equivalent, as you probably know, and this has got a part which consists of only one electron coordinates, and in this term you have got 2 electron coordinates. So, this is usually called as the 1 electron Hamiltonian, and this term as the 2 electron Hamiltonian, and sometimes it is referred to as H1 and H2, and sometimes as F and G, but that is just a matter of notation, okay, depending on which book you will be reading. So, this is the n electron Hamiltonian, and now we are going to seek a solution, and of course, we will be happy if we can get an exact solution. And this problem was posed to Poincaré by the King of England, King of Sweden if the 3 body classical system, the sun, earth and moon, does it have exact solutions, and even in classical mechanics it does not have an exact solution. That is what leads to chaos and other things, right. Now, when it gets down to quantum mechanics and relativistic quantum mechanics, let alone 3 body problem, not even a 2 body problem, not even a 1 body problem, or for that matter even the problem of a vacuum state does not really have exact solution. Okay. It just does not, the solution does not exist, and this is very nicely stated in Brown's book, where he says that if you are looking for an exact solution, then having no body at all is already too many. So, there is no chance of getting an exact solution. Okay. So, now what are you going to do? Try to come up with the best approximation that you can, and if you can come up with a good approximation, then it is going to be a breakthrough, and that is how science progresses. Okay. So, the Hartree-Fock method is not going to give you an exact solution to the n body problem, to the n electron problem, but it will give you an extremely good approximation. Extremely good, again this is a relative term, it really depends on what application you have in mind. What is extremely good at one level turns out to be completely unsatisfactory at another level, and then you have to go beyond the Hartree-Fock. Okay. So, current studies in atomic physics do require you to go beyond the Hartree-Fock, and I will tell you what are the limitations of Hartree-Fock and what is it that you need to go beyond the Hartree-Fock. But before we get to talk about it, let us at least make ourselves comfortable with the Hartree-Fock itself. So, now there is a nice remark that I came across in Herman and Skillman's book on approximate Hartree-Fock solutions, in which they write that let alone the fact that you cannot get exact solutions, but suppose you did. Okay. Even if you could, how much space would it need to write down such a solution? Okay. How much ink would you need? How much storage space would you need? Okay. And just consider this problem, that if you have n electrons and each is described just by 3 parameters, 3 degrees of freedom, right, then you have 3 n variables, okay, which you must specify, and you want to specify what is the electron wave function amplitude over here and then here and then here and here, at least at 10 points you need, if not infinite, right. So, a 10-point grid would be a very coarse grid, nobody is going to be satisfied with that, but you will need 10 to the 3 n numbers, right. And what is 10 to the 3 n for n equal to 1? For n equal to 10, mercury atom 80 electrons. Can you punch this and find out from your calculators what this number is? 10 to the 3 n for n equal to 80, and where are you going to write all this information? Who is going to generate the ink for it, and where is the storage space for it? Okay. So, you have to have some way of dealing with this problem in some practical manner, and the Hartree-Fock method really lets you do that. So, in addition to that, of course, you have got the electron spin, which we know, and the history of the development of Hartree's method is really very fascinating. I think it is worth reading. This was a differential analyzer which was designed by Hartree in 1935, and Hartree played a big role in the development of computers. Initially he was interested in anti-craft gunnery, that was his initial interest, but then there was he also used children's Meccano. I do not know how many of you have played with it, and with these Meccano, which are toys, you could actually do some calculations, and Hartree was inventive enough to be able to use it and do some actual calculations in atomic physics. But then there was a lecture course by Niels Bohr at Cambridge, and that got Hartree interested in atomic physics, and then he started using his brains to come up with this formalism. And then he was helped by his father, who was an engineering professor, but he thought it was fun to do arithmetic, and he helped his son do all this numerical work to get what we now call as Hartree's self consistent field method. So, a large number of computations had to be done, and this was obviously in the pre-computer days, and in fact the first computer, as you know, is the ENIAC, and when this was developed, Hartree was invited to advise, because unless there is somebody to use a good machine, you cannot really develop a good machine. So, all major computer companies, IBMs and so on, they do hire atomic physicists even today, so that they can develop their computers. So, Hartree was one of the first ones of this kind, and Hartree said in 46 that it may well be that the high speed digital computer will have as great an influence on civilization as the advent of nuclear power, and we do know how true it is. So, Hartree certainly made a very important contribution to the development of computers as well, and now we discuss this problem further. This is the self consistency that we are seeking, as I mentioned earlier. You have got the n electron Hamiltonian, which is made up of two parts, the 1 electron part H1 and the 2 electron part H2. Okay. So, these are the two parts of the Hamiltonian, and the Coulomb term 1 over Rij is the 2 electron part. Now, what is going to be our strategy? And this comes from our experience in physics. The variational methods are very powerful. Okay. You build the machinery of classical mechanics on the variational principle. Newton's causality principle is one pillar on which you can build classical mechanics, but you can also do so based on Hamilton's variational principle, right, and build the entire scheme of mechanics. You also know, you use the variational principle to explain how light travels, the Fermat's principle and so on. So, using the variational principle, you can set up a requirement that the variation in the expectation value of the Hamiltonian would be an extremum. Okay. What wave function would make the expectation value of the Hamiltonian an extremum? If you make this question, if you raise this question and find such a function, then one could hope that this would be the appropriate self consistent field solution to the problem. So, this is the variational approach, and this is our strategy now, which is to seek that the expectation value of the Hamiltonian is an extremum. We certainly know how this works, because it does not necessarily mean that okay, it will be a minimum, because when you study only the first derivatives, you could have a minimum, you could also have a maximum, you could also have a saddle point, right. So, there are all kinds of possibilities that one has to worry about, and yes, these things are properly kept track of, and we can get into these details as the discussion progresses. But this is the basic strategy, that the variation in the average value, the expectation value of the Hamiltonian, you seek that this would be an extremum, but when you vary these wave functions, okay, you have got some wave function, it has got some profile, and you change it. So, instead of a certain profile, it becomes somewhat different, right. That is variation, you have changed it. Now, when you change it, you have to make sure that the new shape that the wave function would acquire under the variation that you are trying still generates a normalized wave function, right, because if you integrate the probability density from 0 through infinity over the entire space, you should still get one charge per electron. You would also expect this to be orthogonal to the remaining atomic orbitals, right. So, these are the constraints. So, you are seeking variation, but not arbitrary variation, a variation which will preserve the normalization of each one electron wave function and also its orthogonality to the other single electron wave function. So, these are the constraints, and your problem is now posed as a problem in variational calculus. So, to get this variation in the expectation value of the Hamiltonian, this is the expectation value of a certain operator which is the n electron Hamiltonian, but the n electron Hamiltonian is made up of two pieces, the 1 electron part and the 2 electron part, F and G or H1 and H2, okay, however you call them, right. And you need to determine the expectation value of these two operators, the 1 electron operator and the 2 electron operator, and then seek a variation. So, we first have to learn how you are going to develop a formal structure of this term, which is the expectation value of this 1 electron operator and the 2 electron operator. So, this is going to be the first step in making progress on this problem. So, Hartree and the son Hartree and the dad Hartree, they developed the self consistent field for electrons, but did not take into account the electron spin from the first principles, and then Fock included the spin as well. And I would like to remind all of you once again that spin is something which Uhlenbeck and Goudsmit hit upon accidentally when they were interpreting certain experimental results in Paschen's laboratory, and because they saw some transitions which seemed to be forbidden, and then to explain those spectra they made a guess and they said that okay, there has to be an additional source of angular momentum, an additional source of magnetic moment, and it just worked, but that is it worked for no good reason as was known at that time. But then we know that the reason is the formal existence of electron spin as it comes out of Dirac's relativistic quantum mechanics. Okay, so spin is an integral property of the electron, and then Pauli developed the spin statistics theorem that particles with half integer spins observe the Fermi-Dirac statistics and particles with integer spins observe the Bose-Einstein statistics. So, spin is an integral property of electrons and it has to be taken into account, as we know from relativistic quantum mechanics, and these are the two classic papers in 1928 by Dirac in which he developed the relativistic quantum mechanics, which gave a formal basis to the idea of electron spin. And it is interesting to ask this question, how does statistics, because now we are going to talk about many electron systems and electrons are fermions, so we will apply the Fermi-Dirac statistics. So, how does statistics enter quantum mechanics at all? How does it enter classical mechanics and how does it enter quantum mechanics? So, in classical mechanics basic laws of motion are deterministic. If you know the initial conditions, you can actually determine what the solution is, and you can do it for one particle, you can do it for 10, you can do it for 100, you can do it for 1000. Okay. That you may not need that much information is a different matter, because when you want to talk about the average energy of some system, then you know that each degree of freedom will contribute half kT to the average energy, right. But this is the average kinetic energy which you describe in terms of temperature, and it is coming from the kinetic energy, the half mv square kind of term, which gets added into what finally gives you the temperature of a system, right. But it is not that you cannot determine that average, that kinetic energy of each individual molecule. You can, in principle you can, You do not need to, because it is too much information in which you are not interested, and that is how statistics enters classical mechanics, because you are dealing with a large number of particles and you really do not need all that information. It is not because you cannot get that information, you can, you do not need. These are two different situations altogether. In quantum mechanics, statistics enters even for a single particle, okay, and even for vacuum, okay, because laws of nature are intrinsically quantum mechanical and they are statistical, okay, because quantum mechanics is a statistical theory. So, it is not because that there is a large number of particles that you are working with. Even for a single particle you need statistics, and then statistics enters also through the spin of the particle, okay, because depending on what the spin is, you have to use a different form of statistics. If the spin is half integer, you would use Fermi-Dirac. If the spin is integer, you would use the Bose-Einstein. So, statistics and spin are very closely related, and I will discuss this further. So, let me first deal with a 2 electron system. Okay. You interchange these 2 electrons. So, there is one electron at coordinate q1, the other at q2, and I is the interchange operator, it swaps them. Okay. The interchange operator swaps them. So, you begin with a 2 electron system, apply the interchange operator, okay, and now you apply the interchange operator on this again, swap it one more time, you get this, you get what you started out with, right. So, 2 interchanges, I operating on psi q1 q2, and then another interchange operator operating on the result would regenerate the original system that you began with. Now, these 2 electrons are completely identical to each other, okay, you cannot distinguish between them, and that is the main difference between classical particles and quantum particles. When you deal with classical particles, you can sort of put a color on them or a number or some name, and you can say that this is particle A, this is particle B, but that is not how particles in nature really are. Elementary particles are indistinguishable from each other, okay, you cannot really put a label on that, and this is why this 2 electron wave function is sometimes called as a geminal. Do you know what a geminal is? You know what Gemini is? Have you seen the Gemini constellation in the sky? Okay, it is a beautiful part of the sky, okay, and there are 2 lovely stars, Castor and Pollux, in this constellation, and they look so alike, so similar to each other, so they look like identical twins, okay, which is why this is called as Gemini. So, Gemini refers to twins, and these 2 electrons that we are talking about, psi q1 q2, these 2 electrons are completely identical to each other, they are completely indistinguishable from each other. Castor and Pollux, actually you can distinguish between them, okay, one is Castor, the other is Pollux, you can't do so with electrons, but they are indistinguishable just like twins, okay, which is why a 2 electron wave function is sometimes called as a geminal. Not a very common usage, but not uncommon either. So, you have a 2 electron system, you interchange twice, you recover the original configuration. What this means is that a single interchange can only change the phase, and it can give you a result when you interchange q1 with q2 by a single interchange operator, the result can be either plus or minus, because when you interchange it one more time it will be the same as the previous one. Okay. So, this is what we have got, that two interchanges e to the I 2 alpha would give you 1. So, e to the I alpha would be plus 1 or minus 1, and accordingly this angle will be either 0 or pi, right. So, there are two types of particles in nature. One are the fermions, which have got half integer spins, whose wave function would change sign under the interchange of two identical fermions. But if you interchange two identical bosons, the wave function will remain invariant, the sign will not change. Now, there is this intimate relationship between spin, statistics, and the sign of the wave function on interchange. These three things are intimately connected to each other. Okay. They all go together, the spin being half integer or integer goes with the statistics that the particles would observe, and this goes with what would happen to the sign of the wave function under the interchange of two particles belonging to the system. These three things go hand in hand together. Now, I quote from Tomonaga's book, in which he points out that relation between spin and statistics is apparent, but hard to understand. And an even more comprehensive quote, which some of you might have come across, is due to perhaps one of the finest of physics teachers, Richard Feynman, and he says in his volume 3 that it appears to be one of the few places in physics where there is a rule which can be stated very simply, but for which no one has found a very simple and easy explanation. The explanation is down deep in relativistic quantum mechanics. You can say very simply that, okay, if the particles are half integer spins, they observe Fermi Dirac statistics. If they are integer spins, they observe Bose-Einstein statistics. But to get to the bottom of this issue, why this, okay, one really needs to get into relativistic quantum mechanics in a fairly comprehensive way, and that is a challenging topic by itself, but I will recommend Tomonaga's book for this, The Theory of Spin. It is a very nice book, some of you might have come across, or if you haven't, you will enjoy reading it. So, anyhow, we accept that this is what it is, and under one interchange, electrons being fermions, the sign would change. Okay. And now we talk about a 2 electron system. The 2 electron system is the smallest many electron system, and if we can develop a formalism for 2 electrons, we will know how to extend it to many electrons. So, we begin with the consideration of the smallest many electron system, namely the 2 electron system, and we write the 2 electron germinal wave function psi q1 q2, which we know must change its sign when you interchange the two particles. Okay. And an obvious way of doing it would be to write it as a product of these one particle wave functions u1 q1 u2 q2 minus u1 q2 u2 q1. Okay. Because if you interchange q1 and q2, this changes sign. So, it meets our essential requirement of an antisymmetric wave function. That is what an antisymmetric wave function means. Fermi Dirac wave functions are antisymmetric, because when you interchange particles, this sign changes. So, this is an antisymmetric 2 electron wave function, and it is written in terms of the 1 electron wave function, and I have written this 1 electron wave function more fully because the wave function is the coordinate representation of the state vector. Okay. So, This is the coordinate representation of the state vector in the Dirac notation, which the wave function is. Okay. The state vector is described by a complete set of measurable physical properties, the 4 good quantum numbers, which are n, l, ml and ms for the electron, and its coordinate representation gives you the one electron wave function. This is inclusive of spin, and there are therefore 4 quantum numbers. Okay. Now, if you look at the de Broglie-Schrodinger notation, the UIQJ, notice that the subscript here I represents the set of 4 quantum numbers, and the argument of the wave function, which is Qj, represents the set of 4 degrees of freedom, the 3 space variables and 1 spin variable. Okay. So, the arguments Qj are a set of these 4 coordinates, and the subscripts are the 4 good quantum numbers. Okay, that is the notation. Now, it is important to recognize that we are treating the 2 electrons as indistinguishable. So, you cannot separate one from the other, but the particles are still elementary particles. So, this is a very nice combination of ideas. The elementary nature of the electron is not challenged here in this concept. Okay. But you cannot distinguish one from the other, because normally when you talk about an elementary particle, you talk about the particle as though it has got a complete separate identity, which is the fundamental identity of a fundamental particle, right. But that identity is lost when you are dealing with a pair of electrons, because you cannot say that this is electron A and the other is electron B. So, where is the identity? So, this is the combination of these 2 ideas, indistinguishability and the electrons being elementary particles, and you have to use these 2 ideas without any contradiction in your mind. Okay. So, the electrons will be treated as elementary particles, but they will be considered indistinguishable from all the other electrons in the system, and this is our representation of the electron coordinates and quantum numbers. You can write this easily as a determinant u1 q1 u2 q2 minus u1 q2 u2 q1, right. And if each of these 1 electron wave functions is normalized, then you can see very easily that you will have a normalization 1 over root 2. Okay. So, you can easily write this as a determinant, and in this determinant the rows and columns are labeled by q1, the first column, the second column by q2, and these are the coordinates. Okay. The rows are labeled by the subscripts, this is subscript 1, this is subscript 2. Okay. So, the rows correspond to the set of 4 quantum numbers, which are the occupied states of the electrons. So, this is called as the Slater determinant, named after John Slater, and you will see that the Pauli's exclusion principle is automatically built into it, because a determinant vanishes if 2 rows or 2 columns are the same, right. So, no 2 particles will have the same set of quantum numbers, which is Pauli's exclusion principle. The antisymmetry of the wave function is also inbuilt into this representation, because if you interchange 2 rows, the sign of the determinant will change, right. So, it automatically takes into account the usual features of a many electron wave function, and you can easily extend this not just to 2 electrons, but to n electrons, and then you have got n rows and n columns and a normalization of 1 over root factorial n. So, this is a straightforward extension from a 2 electron system to an n electron system, you can try to develop a determinant for a 3 electron function, do it by hand term by term. Okay. You will find that there are factorial 3 ways of doing it, 6 ways of putting 3 electrons in 3 different systems, right. So, the rows are designated by the 1 electron state. So, the electron configuration is spelled out, and this also spells out the occupancy of single particle states, that if you have got an energy spectrum in which there are hundreds or even an infinite set of single particle orbitals which are solutions to the problem, not all of them are occupied. So, if you have got a 2 electron system like the helium atom, you can have 2 electrons in the 1s state, one with 1s up and 1s down, but you can also have 1 electron in the 1s and the other to some excited state like 2s, 3s, 4s and so on, right. So, that will give you a different configuration. So, the first configuration had 2 electrons in 1s. So, the occupation number of 1s up was 1, 1s down was also 1, and the occupation number of everything else was 0. Whereas, if you have 1 electron in 1s and the other in 2s, then the occupation number of 2s now becomes 1 and the rest becomes 0. So, the occupation numbers, and this is the language of second quantization which also one uses in many electron theory. In second quantization you deal with the occupation number states, and you can see how the Slater determinant expression can easily be adapted to the occupation number formalism. So, essentially what the Slater determinant does is to spell out the occupancy of the single particle states, and it incorporates the usual features of a many electron system, the Pauli exclusion principle, the antisymmetry of the wave function. These are our designations, and you can write the spin orbital. This is called as a spin orbital. This is the orbital part and this is the spin part, and which is why it is called as the spin orbital, okay, because you can factor this spin orbital UIQJ into an orbital part and the spin part, okay. So, this is the spin part and this is the orbital part. So, the UIQJ are typically called as spin orbitals, and the matrix elements of the Slater determinant are essentially the spin orbitals, in which the columns are those which correspond to the coordinates, and the rows correspond to the single particle states which are occupied, and each spin orbital then is a measure of the probability amplitude that an electron at space spin coordinate Qj is in the quantum state n, l, ml, ms corresponding to the ith row, okay. So, that is the notation, that is the designation of the states, and this is how a Slater determinant is written. You are of course aware that there are factorial n ways of permuting the n indistinguishable electrons in n quantum states. So, you can also write this as you can write all the elements along the diagonal u1 q1 u2 q2 un qn and then begin permutations, okay, and carry out all the permutations, but every time you permute, every time there is one interchange, you will have a change of sign, okay. So, depending on the number of interchanges which go into a permutation, you will have a -1 to the power p phase factor, and you must sum over all the permutations, and there are factorial n of them. So, you have to sum over all the permutations for p going from 1 through factorial n. So, you can write the Slater determinant equivalently also in this notation. It is the same as the Slater determinant, right, and this operator in this box is sometimes called as an antisymmetrizer, because what it does is to take this direct product of the diagonal elements and antisymmetrizes it, okay. So, this is sometimes called as an antisymmetrizer. So, this is the antisymmetrizer operator. I will stop here for this class, and we will begin from this point in the next class. Questions?
So how did we exactly separate the spin orbital and the space part?
Okay, the spin orbit coupling does give you a net angular momentum, but these are distinguishable properties, like how you define angular momentum. When I said that angular momentum must be defined in such a way that when it is subjected to rotations it follows a certain law, okay, and it is not going to follow that law if you do not subject the orbital angular momentum and the spin angular momentum together. Okay, this is what we did in unit 2. So these are two separate sources of angular momentum, they are completely independent of each other, okay, and they have their eigenfunctions. One is an eigenfunction of L square Lz, the other is an eigenfunction of S square and Sz, and together they give you L plus S equal to J, and both the eigenfunctions of L and S must be simultaneously subjected to a rotation. So the separation comes from the fact that these are two independent sources of angular momentum.
Suppose in some situation we have a non-zero L dot S term, then
that doesn't matter, that you have a non-zero L dot S term. Okay, I understand your question. Like S orbitals, okay, S orbitals have got L equal to 0 and J will go from 0 minus half modulus to 0 plus half modulus. So there is only one state which is available, okay. Now that is only the eigenvalue of L square, okay, but that does not prevent the electron from having the property of orbital angular momentum. It has the property of orbital angular momentum and it is in one of the states corresponding to L equal to 0, but it is an independent property which is completely independent of the spin. So these are two independent sources of angular momentum, J1 and J2, which couple to give you J3 or the net J, which is L plus S equal to J, and their respective eigenfunctions are the spin part and the orbital part. The net wave function is a product of these two. Any other question? Okay, so let me stop here and we will resume from this point tomorrow.